All right, let's do some trig integrals today. And in this particular video, I want to focus just on sine and cosine. I want to remind you that the derivative of sine is cosine, the derivative of cosine is negative sine, and we do know the Pythagorean theorem identity that says sine squared plus cosine squared equals 1. This particular gem is going to allow us to rewrite sine squared as cosine squared and vice versa. All of these, as a reminder, just are the power rule. That's it. They're just the power rule. You're just doing use substitution and making all of these things into the power rule using these facts. Okay, so look at this first one. This first one is the easiest one. There's nothing really to be done on this first one. All you have here is like, well, look at this. If u is sine x, du is cosine x dx. You love the fact that there's a cosine here. There's a cosine here. This, boom, done. U cubed du, and you know that integral is u to the fourth over 4 plus c, and then u is sine x, so this is sine to the fourth x over 4 plus c. And there's nothing really to be done on this particular trig integral. It had the exact setup you wanted. It had sine to some power, and then you had a cosine chilling out right here, but it functions as the du, u cubed du. Again, you could go through the use substitution if you need to, but hopefully you can look at this thing at this point and be like, oh man, this is amazing. That cosine, we love that that cosine's there. If the cosine wasn't there, I'm not sure what I would do. Well, that's what we have to work on. Okay, let's look at this next example. So I left the sine as cubed, but now I'm making the cosine cubed as well. You're like, oh man, what do? Well, here's the process. We know that if we want to make u sine, we know that du has to be cosine. So we need a cosine out here. So what you can do is you can rip off a cosine. So leave the sine alone, rip off a cosine from cosine cubed, leaving cosine squared, and let's put this cosine off to the side. We know that eventually that's going to be our du. Well, if that's our du, then our u has to be a sine. So what do we do with this cosine squared? Well, it turns out I can rewrite that as sine squares. So if cosine squared is just 1 minus sine squared. Let that cosine chill out. Remember, we ripped that off on purpose, full knowing that we're going to use it eventually as the du. Now I have my full-fledged substitution. If u equals sine x, du equals cosine x dx. And then what do I have here? I have u cubed times 1 minus u squared times du. I changed the cosine squared to a sine, full knowing that I was going to use u as sine, and then this extra cosine x was going to be then the du. And so this whole thing is then the integral of u cubed minus u to the fifth du, and I changed successfully the trig integral into some easy power rule. This integral then is going to be u to the fourth over 4, so that's sine to the fourth over 4 minus sine to the sixth over 6 plus c. Again, the integral of u cubed is u to the fourth over 4, u to the 6 over 6, and I just put in u because I was kind of running out of space there. Again, this trig integral became this. Okay, how about this one? What if you don't have a cosine? Here you had a cosine that you loved. Here you ripped off a cosine, changed the remaining cosines to sines, and then went to work. What about over here? What if you have sine cubed? Well, we can do the reverse. We can rip off a sine, and we can change the remaining sine squares into cosines. So we take a sine off to the side, think of that as our du, and then we can rewrite this as 1 minus cosine squared sine x dx. Okay, so we can multiply this sine in then. This is sine x minus cosine squared x sine x. And then we can just do that integral. Okay, the integral of sine x is just negative cosine x And then here, there's your u, and there's your du with that negative sign. And then this is going to be plus. So off to the side here, u is cosine x now. Du is negative sine x. And this integral then is really just integrating u du. Well, the u du is then just cosine cubed x over 3. I know I ran out of space there. I'm not really happy with not being able to show all of that work, but there's your u squared. Negative sine is du. So then I'm integrating u squared du. The integral of u squared du is u cubed over 3, where u is cosine, and so we have this, of course, plus c. Okay, let's do another example. So what if I had sine cubed and cosine squared? You're like, okay, if I ripped off a cosine, I'd only have one cosine left, and I couldn't change a cosine into a sine using this identity. So I can't rip off a cosine, ooh, but if I ripped off a sine, then I could change the remaining sine squares into cosine squares, and then I'd be in luck. Okay, so let's do that. Let's take this and rip off a sine squared, a sine. So don't do anything to cosine, and take one of these sines and throw it over here. Leave that guy parked right there. And then let's change this sine into cosines. So that's just 1 minus cosine squared times cosine squared times sine x dx. And now the process is kind of done. Here is going to be du, and then there is u. Now there is a negative sign issue because sine x isn't the derivative of cosine. Negative sign is. So I'm going to put a negative sign out in front. And this is just 1 minus u squared times u squared times du. But that whole integral then is just negative u squared minus u to the 4th du. So then it's negative. The integral of u squared is u cubed over 3, cosine cubed over 3, and then a minus and a minus make a plus, cosine to the 5th over 5. Okay? The whole process on any of these is what? Okay, you take a look. And hopefully at this point you're like, okay, how do we know which one to rip off? The cosine or the sine? Well, it's always going to be the odd one. And if there are two odd ones, then it doesn't matter. This one's beautiful because the cosine is just chilling right here and there are no other cosines. So it's just u cubed du. This one, I ripped off a cosine, leaving cosine squared. I changed cosine squared into sine squared stuff. Then everything left was sines, and I had a cosine for my du, and they were then u's du. This one, I didn't have any cosines. So you have to rip off a sine, change the remaining sine squared into cosine squares, and then you have u stuff, du. Eventually this became 1 minus kind of u squared du, which then went to this. Here I can't rip off a cosine because I'd only leave a cosine, and I can't change a cosine into a sine. I have to change a cosine squared into a sine squared. So see this cubed, take off a sine, change the remaining sine squares into cosine squares, and so then you have a bunch of cosines with your du as the sign. And the negative sign is just from the fact that you really needed a negative sign out in front. Okay, these are probably the most popular ones. There are two other ones I want to discuss just for full disclosure. So number 5 is gross. You can mark it down. I'm not putting this on the test. Not on test. I think this one is ridiculous, just because it would just be so much algebra and it would take forever. But see how this is a sine squared and a cosine squared, and they're both even? Both evens is garbage. It's going to get ugly because you can't rip off a cosine and you can't rip off a sine because you'd be only leaving one power, and you can't change sine into cosine. You need to change sine squared into cosine squared. So it turns out what you have to do is the silly double angle formula for both of them. And then you're going to end up having to repeat it. I'm not going to go through this whole process because it's long, and that's why I'm not putting it on the test. But Sine squared is equal to 1/2 minus 1/2 cosine 2x. Cosine squared is 1/2 plus 1/2 cosine 2x. You'd have to multiply all of this out and get some nasty looking thing. And then you'd end up still with the cosine squared 2x. And you'd have to rewrite that with the same trig identity. And then finally, you'd be able to integrate it. Oof. If you really wanted to know this one, you would look it up in a table, look it up, or just have some software. Have some software hook you up. Okay, I'm not going to put that one on the test. Something like this, well, you'd be able to do it. It would also be really ugly, not on test. This one is more doable, just because the power is so darn big. It's still, you look at the odd power, this sine, you're still going to rip off a sine, leaving a sine to the 6th, cosine to the 4th, and then you ripped off one of the sines, so put it over here. You know this is going to be du. It means all these then are going to be cosines. So take this sine and rewrite it as 1 minus cosine squared. Right? That's sine squared. That's sine to the 6th. Sine to the 6th. Sine squared cubed. Okay, so it's really ugly, but it is finished now, other than me doing some algebra. All of these things are going to have cosines. This is going to be a sine. If you really multiplied this out and cubed it, you'd have to go through that whole process of what that would be cubed, then multiply in cosine to the 4th to each one of those terms, and then all of them would have u's, and that would be negative du. Again, it's doable. It would just take some time. There'd be lots of negative signs and factor mistakes, but I'm not going to put that on the test. These two scenarios, when the power gets really big, and if both are even, that's when trig gets messy with sines and cosines. Okay, so these versions you should know how to do, but I'm not going to put on the test. The most important versions are kind of these versions where the powers are reasonable, they're cubes and squares, and you have to recognize, in this case, rip off a cosine, u du. In a case like this where cosine's even and sine is odd, you have to rip off the sine. Here you don't really have a choice. You just got to rip off a sine and change the remaining signs into cosines. Okay? All of them end up as the power rule. And again, this is the first video for trig integrals. This one's just focused on sines and cosines. The next one's going to be secants and tangents. The strategy is identical, except you're just dealing with secants and tangents. Their derivatives are a little bit different, and their Pythagorean theorem is a little bit different, but the strategy is the same. You're still going to take a whole bunch of like integral of tangent cubed secant to the 4th and rewrite it so you can do it using the power rule. Okay?